Now that we understand current and resistance, we have one final thing to go over before we move on. This lesson is going to act as a perfect segue into the next module on circuits because we're going to start by creating one of our very first closed circuit diagrams. You might remember we went over a couple of closed circuit diagrams before when we were dealing with capacitors, specifically multiple capacitors in parallel or series. But there's a key difference here, and that difference is when we were dealing with those capacitors, we were concerned with measurements once all charge had stopped flowing. In other words, once there were no electric current in any of the wires. Here we concern ourselves with the exact opposite. We want to know exactly what's going on while charge is flowing. We don't care once charge has stopped flowing. In this case, charge would essentially have stopped flowing once the battery dies and the potential difference across the battery drops to zero. That's not really interesting. There's nothing going on. It's just nothing to measure. We also have another circuit symbol to add to our collection. This symbol is the resistor, and it's symbolized by a sort of squiggly line. On the surface, it seems the symbolism is such that if you could imagine a charge moving through this element, its movement is technically being resisted because it needs to go through all these zigzags, a lot of length and a small cross-section. A resistor is just a conductor with a high amount of resistance, way higher than the wire it's connected to usually. Now how would we create a resistor? We want a high resistance, so this means we need a metal with some good resistivity like nichrome, and we want a long length, so L is large, and a small cross-sectional area, so A is small. The only parameter that potentially gives us a problem is the length. We can't just span wires across our entire laboratory just to get the large resistance we need. Instead, what we like to do is take all that length and confine it to a small space. So one of the oldest ways of making a resistor, which is still quite common even today, is to take a cylindrical insulator and wrap thin conducting wire around it. This is called the wire wound resistor, and the benefit really shows when we increase the number of turns on the wire. The length of the wire increases, so the resistance increases as well, but the overall space that the resistor takes up stays the same. Also, looking at it from the side, it sorta kinda looks like our circuit diagram symbol for a resistor too, don't you think? So imagine now we have a circuit that contains just a resistor and a battery. The resistor has some known resistance R, and the battery has some known potential difference delta V sub B. But there's one other component here that we haven't discussed, and that's what we call a switch. A switch is just a break in the circuit. The circuit is full of essentially conducting material everywhere, except right here. We have an insulator which splits the circuit components, so there's no way current can flow through this circuit. But excuse me sir, what about this gap here? Don't worry about that one. We'll discuss that in a lot of detail in the next module. For now, just assume there's no gap there, and the only actual insulating gap is at the switch here. Then as soon as we flip the switch, the conducting circuit is closed, and current is able to exist through the circuit. Charge is able to flow through the circuit. The electric current in this circuit is going through the circuit in the clockwise direction, and if we want the magnitude, we can find that too, by taking advantage of the definition of resistance. The resistor's resistance is R, and equal to whatever the magnitude of the potential difference across the resistor is, divided by whatever current goes through the resistor. In this case, the potential difference across the resistor is just whatever the potential difference across the battery is, up to a sign. What we usually do in circuit theory is treat the electric potential across empty conducting wire as just staying constant. That means the electric potential at point P1 here is the same as the electric potential at point P2. The reason why is the resistor's resistance far surpasses the amount of resistance in the empty wire. We design empty wire by itself to have small resistances by keeping a large cross-sectional area and a small length. So we can practically ignore any resistance in the empty wire and say the resistance in the circuit is only due to this resistor here. If we treat the empty wire as having no resistance, then it's also at constant potential, since the potential difference across it would be I times 0, or just 0. It's only once we hit the resistor or battery that the electric potential starts to change. Also, we can say the electric potential at point P3 is the same as the electric potential at point P4 by the same logic. But these two pairs of electric potential aren't equal to each other, because the potential difference across the battery is, well, just the difference in potential across it, right? Vp1 minus Vp3. The potential difference across the resistor, if we're thinking about the direction of the current or the movement of the positive charge, is just Vp4, the final potential, minus Vp2, the initial potential. Because of the equalities above, this is just Vp3 minus Vp1, or just the negative of the potential difference across the battery in the direction of the current. Now there's a lot of stuff going on the screen here, so I just want to take a moment to pause and reflect on all of this. Our original goal was to determine the magnitude of the current going through the circuit. We already know the correct direction, we just want the magnitude. We wanted to find the current using our definition of the resistance across the resistor, but there is just one problem. While the resistance R is a known, we don't necessarily know the potential difference across the resistor delta V sub R. So in that case, we don't have enough information to determine the current. But I made the bold claim that actually the potential difference across the resistor is exactly the same as the potential difference across the battery, in terms of magnitude at least. We proved this claim is true as long as we make the assumption that the electric potential is constant along empty conducting circuit wire, which we saw was a reasonable assumption to make. Our end result then is that the potential difference across the resistor is actually the negative of the potential difference across the battery. And this is actually quite a profound statement, as we'll see in the next module. The potential difference across the battery is positive in the direction of the current, since the positive terminal is at a higher potential than the negative terminal. This means the potential difference across the resistor is a negative value. Any charge that moves across the resistor actually experiences a decrease in electric potential, not a gain. We'll see why understanding this is so important in the next module, and that's why I wanted to be very explicit with what we were dealing with here. But the end result of just finding the magnitude of the current is quite straightforward in itself if we know the potential difference across the battery. Just considering magnitudes here, we can replace the potential difference across the resistor with the potential difference across the battery. Then the current through the resistor, or the current through the entire circuit, is just the potential difference across the battery divided by the resistance of the resistor. Now let's consider energy for a second. Consider a small amount of charge Q moving from the positive terminal all the way to the negative terminal, while passing through this resistor too. What is the change in energy of this charge as it moves through this path? The change in energy is really just the change in electric potential energy of the charge, delta U sub E, or just Q times the change in electric potential. The change in electric potential that the charge experiences, delta V sub C, is its final electric potential minus its initial electric potential, or really just the potential of the negative terminal of the battery minus the potential of the positive terminal. And this is just the negative potential difference, or the negative voltage across the battery. Now, this is the change in energy of the charge. We see the battery itself has electrochemical energy that it passes on to this charge, and the charge loses electrical energy, Q delta V sub B, in moving across this resistor. The charge is losing energy because Q is positive, and delta V sub B is positive. So negative those two multiplied together is a negative value. The change in energy of the charge is negative. But where does all this energy go? By conservation of energy, the energy this charge loses has to go somewhere. It can't just disappear into nothingness, right? The energy is delivered to the resistor, and the resistor immediately releases this energy in the form of heat. It doesn't store the energy in any way like the way capacitors or batteries can store energy. Assuming there's no other mechanism of energy transfer, the resistor just releases Q delta VB worth of heat, whatever electrical energy was delivered to it. So just recapping, the battery passes on its electrochemical energy to this small charge, which passes off its electrical energy to this resistor, which then releases that energy to the environment in the form of heating up the surroundings. That's not super exciting for just a single small charge Q moving through the circuit, So let's think of this energy transfer during the operation of a closed circuit. Imagine this amount of energy transfer occurs over the course of some small amount of time, delta t. Then the amount of energy released by the resistor per unit time is just the energy released, Q delta V, divided by the amount of time to release that energy, delta t. But if you think about it, Q over delta t is just the current in the circuit, because the resistor is like a crossing point for the charge. Whatever charge passes through the resistor, if we call it Q, and it takes a time delta t to cross that resistor, then that charge divided by the amount of time taken is just the same as the current in the circuit. Before, we were focused on charge passing a single cross-section over some delta t, but here, whatever charge crosses the resistor as a whole during delta t is an equivalent concept. Then the amount of energy released by the resistor per unit time in the form of heat is just the current I times the potential difference across the resistor, delta V. This is also just the power released by the resistor, or the power delivered to the resistor. The power released as heat by the resistor, then, is the current flowing through the resistor times the potential difference across the resistor. We just derived it here for resistors, but this expression is actually true for any DC electronic device, like a motor or an LED or something like that. But let's think again to where all this energy goes. The majority of the time, the energy is just released as heat. The resistor heats up the surrounding air, like how the large resistor in your toaster oven toasts your bread. Sometimes, though, you can also have resistors releasing energy in the form of light. Really, a light bulb is just a fancy resistor that releases some energy in the form of heat, but some of the energy is also released in the form of light. This is why if you've ever touched a light bulb that's been on for a while, it feels really hot because they're in the process of heating up the surrounding environment. Also, if you think about a computer that's working really hard, like for example, maybe you're watching a high definition video online on some obscure physics website nobody's heard of, then you might notice your computer start to get hot too. That's because there are a bunch of resistors in your computer circuitry that release energy in the form of heat, but they're necessary in order to regulate precise currents through your computer's sensitive electronic components. Going back to our expression for the power delivered to a resistor, or the power released by a resistor as heat, we can express this in terms of the resistance too. Recalling that the potential difference across the resistor is just the current flowing through the resistor times the resistance, we can express delta V as just I times R. Then substituting for the potential difference, the power delivered to the resistor can also be called I times IR, or just I squared times R. Or if we substitute for the current from there, the power is delta V squared over R squared times R, or just delta V squared divided by R. These three expressions might remind you of the interplay with the three expressions we had for the energy across a capacitor. They look kinda sorta similar. We have three variables at play, and each equality contains some permutation of two out of the three variables. Once again, when we're working with problems, the trick to these expressions is to use whichever one contains some variable that's constant or not changing. And we'll go over how that's done in some of the exercises and problems.
Let's get this over with. 1, 2, 3, 4.